I'm recording the lecture now. Please let me know if you have problem or you don't want to be in the recording in any shape. If there is a problem, let me know. Otherwise, I'm assuming that everyone is okay with the lecture recording. Last week, we at the end of the lecture, we had a brief review on matrix, basic algebra application, and a very, very short review, actually, or introduction to matrix application and algebraic operations like summation, sum, add, sum, multiplication, determinant, and inverse matrix. Today, we are going to extend that slightly more to geometrical application and vector analysis. Very, very brief again. I'm not going into details. We review as much as we need to have a better understanding of robot structure and movement mechanism. Okay, so before I start this part, I want to make a relationship between a matrix and geometry, okay? Between matrix and geometry. So to do so, imagine, I just use this space to write. Sorry, I didn't leave any blank space, but I use it here. In a, if you look at coordination system, every point in the coordination system can be indicated using components of x and y, components in x and y direction. So if I have a vector like this from origin to the end, I can indicate the end point based on, so if this is point P, I can project P on x-axis and project P on y-axis. So on x, I get this distance. On y, I get that distance. So if I call this xp and this one yp, I can represent that point with a pair of numbers like xp and yp, representing projection of the point on x-axis and y-axis. We also can extend this to three-dimensional. If I have a three-dimensional space, sorry, I think it's better to change the color to black. Yeah. If I have a three-dimensional coordination system like x, y, and z, a point can be projected to x, y, and z. So if this is point P, xp, yp, and zp. So I will have xp, yp, and zp representing that number. We can model these as a matrix, as a vector, or this. So as a vector, it will be this one, the two-dimensional, will be represented by a matrix of a vector of 2 rows. And can I ask just if you have your microphone open, please mute your microphone because it's making a loop and might make it noisy for others to hear. Thank you very much. And for the three-dimensional space, it will be xp, yp, and zp as a point. So this is how we relate matrices to geometrical space or to coordination system. This is a starting point, okay? That's why, therefore, I can, every point or every vector like D in a three-dimensional space, if it has x, Y, Z components, like A, this one is B, this one is C. It can be represented as a D, A, B, C in direction of I. I is the unit vector in the direction of X. J is the unit vector in the direction of Y. And K is the unit vector in the direction of J. This is kind of tradition in mathematics to show it in this way. Also, they can represent that as a metric, as a vector like A, B, C. Okay. Now we are going to invent actually a method to use matrix algebra, basic multiplication, addition, operations on matrices to represent different transforms in a three-dimensional geometrical space. Okay, we try to combine these two because matrix operations and softwares for matrix operation and tools we have for matrix operation mathematically and software based are, it provides us a rich library of different capabilities we can use. So we combine these two together to create a new tool. What you see here as H is a simple extension to represent that point, to represent this transformation. I'll talk about this more. You'll see more about this H trans ABC in more detail. So don't worry about structure, why it looks strange, what is this 1, 0, 0, 1, and 1, 1, this combination. We'll talk about that more when I get to the other slides. So, I left space here. I forgot about that. All right. So, example, just to give you a very, very simple example of what I have. So, if I have have a look at two-dimensional. If I have a point like P located at XP and YP, if I move that point, or if I move this coordination system, these two are, this movement is relative. You can talk about both, okay? So I'll consider movement of the coordination system. Let's say my coordination system, which I call coordinate system of X and Y. If I move it to, I just move it like D in direction of X. So this point, center point, will be moved D in direction of X. So I'll get another coordination system as X prime, Y prime. Now the question is, if I knew that location of my position P in coordinating system X and Y was X and P, can you tell me what would be coordination of point P in X prime and Y prime system? So here, when I project it, it will be this. But when I want to, when I look at this vector, it will be here. But now I'm looking at this vector. Do you know, or can you tell me what would be the coordination of point P for system Y prime? So the question is, if we know coordination or coordinates of P in the system or in the coordination system X, Y, what is coordinate, or what are the coordinate value, or what is the coordinate of P in the coordination system X prime, Y prime. This is an essential thing in robotic, right? In robotic, we know where is our big robot, and we know how much our end effector has moved in direction of X or Y or Z. Now I want to know what would be the coordination of the system in the tool coordinating system if I know what is the coordination of that point in my base system. So transferring addresses from one coordination system to another coordination system, which is the problem, okay, which is the question. So we are going to deal with this. We are going to talk about this issue today, how we transform coordination of points or pose of the three-dimensional objects from one coordinating system to another coordinating system, okay? So for example, if I move coordination system, or if I move, instead of this, if I do it this way, look, if I change the whole story to this, if I say, well, I'm going to move the vector like D, so what would be the coordination for this one? Okay, so if you want to make this generalized, you have to divide movements in 3D space in two types. Movement in 3D space, similar to what we had in robot joints, very similar to those. You remember, in robot joints, we had two type of movements. One was translational, means moving from one point directly to another point. It can be in any direction, right? It can be in any direction. This would be translational. So from one point, just taking the object, moving it directly to somewhere else. The other one was rotation. So if I have an object with a shape, whatever it is, if I take that object and rotate that object in a direction, depending on what direction you rotate, versus X versus Y versus Z, there will be different situations for your final pose. Your current orientation will change to something else depending on how much in degrees and around what axis you do the rotation. Okay, so to present this, if I ask you a very basic simple question, so if I have, so example, if we move point P 10 and 3, okay, if we move point P, if we move point P 3 centimeters, so if I consider this as meter or centimeter or unit of length, 5 unit of length in direction in X direction, what would be the new coordination? Coordination for P. Very simple, super simple. So if I have a point at 10, 3 here, 10, 3. If I move this point P 5 units in X direction, what would be the coordination of this new point? Can you please type in? Super easy, I know, but I want to keep everyone active. So what would be the coordination of this point? Okay, so it was at 10 and 3. Now I'm moving that point 5 steps in in positive X direction. I had to say that. You could ask me, why did you go on right? Why didn't you go on left, right? In 5 direction, yes, it's 10, and you are going further 5 steps, so it will be 15 and 3. Okay, I can repeat that question if, and I tell you that we move 2 steps in. Okay, we continue to move. We continue means from point P prime 2 steps in positive or negative Y direction. So what would be P second? So negative 2 comes down. It will be here, P second. What would be the new one? Yeah, it means your Y will be reduced by 2. Your Y will be reduced by 2. That's how we address points. So in robotic, similar. So I'm trying to build up something very similar. You see, it's super easy now. If you have a point somewhere, if I tell you go 5 steps to right, then 2 steps down, you know where are you now. If you can keep track of changes, you can keep track of locations as well. Right? So I can go and just change everything and make it like, if I have a point located at, if we move, sorry, another example. I wish I had something to clean everything up here. I don't know. You can see. All right. Similar to whiteboard. Okay. So if you have point at -5 and 8, if we move this, 10 steps to positive X and 10 steps to negative Y, what would be the P prime? Exactly. 10 step to, so what I have here is, so I have a -5 down here and, sorry, here, -5 here and 8. This is -5, this is 8, my P. After moving 10 steps forward and 10 steps down, so I'll get here. So here will be 5, here will be -2 total. So this is 10, this is 10. Okay, very good, fantastic. Now so we have a brief understanding, and for 3-dimensional will be same thing. For 3-dimensional, just very simple example to make sure we have covered that as well. So if we have a point like P at 2, 6, -7, and we move it like 5, move 5 steps in positive X, 5 steps in negative y and 5 steps in positive z will give me p prime as 5 step positive, so will be 7 exactly. 5 step subtracting this will be 1, and adding this will be negative 2 exactly. So what you do is the point you have like A, B, C, and the movement you have as dx, dy, dz, displacement, okay, depending on positive, negative, you have to add them or subtract. So P prime will be A, so positive, negative plus dx, and B plus dy, and z, or C, sorry, plus d z. So here, since it's negative, this one will be negative. Remember that should include the sign as well, because movement can be in positive or negative direction. Very, very simple calculation. Now, I'm going to relate this into a very simple matrix representation. Very simple matrix representation as we have here. I'm trying to relate this to what we had before. So I can represent this movement using matrix matrix operations like this. I'm sure there should be something to clean everything up. Sorry, my bad. And okay, so in a three-dimensional space, if I represent everything in a matrix form, so my point P will be like A, B, C. If I have displacement, D as dx, dy, and dz, dz, my P prime would be A plus dx, B plus dy, and C plus dc. Okay. If I represent everything in the matrix form like this, 1, 1, 1, 1. Okay. 0, 0, 0. So let's do it proper way to understand. 1, 0, 0, 0, 1, 0, 0, 0, 1. Then I have 0, 0, 0, 1. Here I have dx, dy, dz. See? This is exactly repeated here. All right? And now, if I multiply this into original mix A, B, C, what would be the result? I want to answer. You cannot. Why? Because this matrix is 4 by 4, And what you have is 3 by 1. And we learned that these two must be equal to be able to do the multiplication. And that's 100% true. That's 100% true. Very good. So to solve that, we need to, I know that it's well, kind of weird. I have to add 1 here. Why we are doing this? That's why I said we are going to invent something. This is something we are making up. Okay, we're trying to use our metric skills and bring them into vector algebra. Let's say, or to vector calculation. Page 2702 is the first one, an identity matrix. No, because this last column is not 00001. We have these items. Similar, but not. It's from page 27. Josh, I don't get that. What do you mean it's from page 27? Oh, yeah, here? Yes. Slide 27. Yes, from the previous one. Exactly. Now, if you multiply these two together, now, what would you get? What would be the result? So this one will be 4 by 1. Your result will be a matrix which is 4 by 1. What would be the first component here? Can you do that for me, please? The first component. Do the multiplication. Multiplication means here means this multiplied by this 1 by 1. No, this one 1 by 1, and then add them together. Okay, if you multiply them 1 by 1 and add them together, what would you get? If you add them, you have to add them too. So if I multiply them together, you see it will be 1 times A plus 0 times B plus 0 times C plus dx times 1, which would become A plus dx. Magic, huh? See? Same component. All right. So let's try the second one. So can you please just multiply second row and find this component for me? If you multiply the second row, it will exactly will be 0 times A plus 1 times B plus 0 times C plus dy times 1, which would be B plus dy. Exactly. Thank you very much, Farhan and Paul. So it will be plus dy. And I don't need to even do the calculation. What do you guess will be the third component, even without calculation? Even without calculation, you can guess that the third one is C plus dz. You don't believe that? You can do it, here. 0 times A plus, yes, Paul, you're talking about the next row, right? 0 times B plus 1 times C plus dz times 1. It will be C plus dz. And the fourth element will be The last element will be, yeah, Paul already gave the answer. Yeah, exactly. So 1. The beauty is the results. So if you represent every point at 3D space using this kind of presentation, so three components of vector A, B, C with one extra one at the end. With this operation, you always get similar format, like 3 points with one extra. And I always can ignore that one. This is my real coordination of the next point. Okay, very good. So is it clear to everyone? Any question? I'm sure you have question, and it would be very, very valid that why we are doing this. It was so easier. I could do it. You say what is the current point, and you tell me how and where and in what direction you're gonna move that point. I'll give you answer just by adding. This is more difficult compared with that, right? You have to do matrix operation, matrix a multiplication to find the same thing which I could do just by addition. Do you agree or not? You definitely should agree with that. Yeah, it's much more easier if you do it directly from there. So it will be a very valid question if you ask me why we are doing this. What's the point in that? The point lays in the next step. When we look at for translational move, you're definitely right, completely right. But when it comes to rotation, it becomes a horrible nightmare if I want to do it directly. Not impossible to do, not very, very difficult. But if you want to make have everything in one platform, it will become very difficult. That's why in robotic, people, researchers, people, teachers, engineers have come up with some solution to make it easier to represent. At first, it looks ridiculous. Honestly speaking, first when I learned this, when I was using this, when I just had it, as a student, this is nonsense. Why are they doing this? But after doing the next few steps, I realized that there was a point in there. So they had the point, and point lies in here. I'll talk about that. Okay, I promise to make it clear, hopefully today. So our approach now is to have a translation operation in matrix space using a representation like this. So I have a unit vector. Jordan was right. It was a unit vector here. What I had here was 1, 1, 1, 0, 0, 0, 0, 0, 0. Look at mine. See? This is a unit vector. This is definitely a unit vector. A unit vector here. Well, not always unit vector. Actually, it's a very, very important part. I'll talk about that. Then your translation values, your movement values sitting there. Here you have 3 zeros. We don't touch that. And 1. So this is kind of fixed attachments, fixed appendix to my matrix when I'm doing this translational thing. So we call this a homogeneous matrix. Homogeneous matrix, an operation based on homogeneous matrices. So the homogeneous matrix describes either pose, orientation, and position, or displacement, rotation, or translation of an object. It consists of a 3x3 rotation matrix. It spoiled the story. This is for rotation. In the previous example, did we have any rotation here? No, I didn't say anything about rotation. No, we didn't have anything. It was a point. We moved that point from one point to another point. That's why it was identical. Means rotation of the object you're trying to transform is same, identical, no change. That's why we did not have that. So this is the rotation part, and this is the translation part, or linear, actually. I would say linear movement. Okay, rotation and linear movement. And in one whole matrix, we can combine both together. We can have them both together. So rotation matrix shown by dot and the square one, and 1/3 perspective transformation row. This one. Okay, we use this representation. We try to explain, think about that. We try to explain all those manipulator robots see in industry, the moving things, you know, shuffling items on a manufacturing and an assembly shop with this matrix, with all the, you know, rotations, all displacement, or you know, even later instructions by using this type of matrices. Any question or any suggestion? All right, good. So that's what I said. So when using homogeneous transformation matrix, an arbitrary vector has the following phi1 form. So this is the location. Oh, sorry. This is the current location of the point, or you know, coordination of the score, and you can show it in the transposed form like this. Same was a question. Yeah, transpose of the well, same thing actually. A translational displacement of vector q for the distance d is obtained by multiplying the vector q with matrix h, the matrix h, as we did. So when you multiply this, you will get the displacement. So the translation, which is presented by a multiplication with homogeneous matrix, is equivalent to the sum of vector q and d. In vector space, we do it this way, as I said. So these two will be added, or simply just adding different components at different direction, one by one, pairwise to each other. Or in a simple example, the vector of 2, 3, 2 is translationally displaced for the distance of 4, -3, and 7. You easily can just do the calculation using this, but with this matrix, since your displacement are 4, 3, and 7, you have 4, -3, and 7. These 3 are coming here. And this one is identity matrix, no rotation. This part is just in fixed value 0, 0, 0, 1. So your result will be calculated using multiplication. Multiplying this to this, you'll get this result. So all you're doing is adding up the distances. Exactly. That's what we do, but using this matrix. We are using this matrix, we are using a more difficult way to do a simple thing for a reason, As I said, the main strength of the method comes in when you talk about combination of rotation and translation of movement, like robots. So translational YZ, okay, will be when you have only movement in X direction, you use this matrix. You see in this matrix, again, this part is unique. And here you have only A, 0, 0. In Y direction, same thing here, no change. But at this part, you have 0, B, 0. And you see this part are same, as I said. And in Z direction, again, this part is unit matrix, identity matrix, and this one is 0, 0, C in direction of C. So each component of the last column, first three elements represent translational movement in direction of X, Y, and Z. So write a matrix. What is the homogeneous matrix for the following linear or translational movement? So a movement, translational movement vectors. So I show my movement in terms of vector. So will be, I want to move, so my displacement is -3 to 0, d1, d2, 5, -7, 7, and d3, yeah, different numbers, 0, 0, 0. Okay, let's do a very simple example. For D1, what I have, so I write it exactly as we had. So the rotation part will be fixed. I'm not going to touch that, so it will be 1, 0, 0, 0, 1, 0, 0, 0, 1. And this part is also fixed. I'm not going to change that. Okay. The only part I should focus on is this part for translational movement. I was complaining this thing on the bottom of my display doesn't come up, but now it comes up too much, but now it doesn't come up at all. Sorry. Okay, so this one. For the first one, this is X, this is Y, this is Z. And what I do will be X, Y, Z. So this will be dx, dy, dz, just to be consistent with what I did, dx, dy, dz. Means displacement you want to have. So here will be -3 to 0. This would be for d1. Is it clear? Fantastic. For d2, what I need to do is just putting this in the matrix. It will be 5, -7, and 7. Now, the only thing you need to do, you just multiply this to the original to whatever location it is. Doesn't matter. So your current point, wherever it is, you just multiply this matrix to the current point, you will get the destination. This is like a general operation. So you have a translation matrix to do that. And for D3, how much we are moving? Nothing. It says don't move in X and Y and Z direction. No change. So what I should put here is 0, 0, 0. So in that case, what I'm getting, look at this matrix. It's a 4 by 4 identity matrix. Whatever you multiply this matrix to, you will get the same thing. You will get the same thing. When you multiply this to any point, any vector, you will get the same matrix. So very simple. Any questions so far? No question. We are going to change the tune now. So if there is any question, please, yeah, come in. Otherwise, no question. Very good. So tell me, is it difficult what I said? So from 1 to 3, 1 to 5, or 1 to 10, let's say. 1 to 10, what is the level of difficulty of this so far? And I want everyone to answer me. From 0 to 10, yeah, from 1 to 10 or 0 to 9. From 1 to 10, what is the level of difficulty? So lowest. For exam, Milton, you're so political. 2, yeah, 1, 2, 3. So level of difficulty is very low, right? On average, what I see is between 1 and 3. I haven't seen, just need to practice applying it. We need to practice about matrix multiplication, like what you did last week. So hopefully no one has problem, and it's super easy. If I ask you what is the matrix, you know how to fill out the matrix. If I ask you to do the movement and give the initial point and ask you what is the end point, you just multiply your matrix into the vector. As easy as that. No problem, no issue. Okay? Fantastic. So far, so good. Let's move on. Sorry. Let's talk about rotation. Now we're trying to formalize rotation as well, similar to what we did for, well, like what we did for the translation. Think about rotation. Think about rotation. How many different rotations are possible to apply to a 3D 3D object or item? Okay. If I think about dividing rotation into components similar to translation, my rotation either can be around x-axis, sorry, like this, means you keep x and y. I wish I had the three-dimensional thing. So like this, you see, you keep everything is fixed, but you rotate one axis like that, okay? So I keep it like this, and I rotate one axis like this, okay? That's what we do in the rotation around x-axis, or rotation around y-axis, or rotation around z or z-axis. So in y-axis, if I have rotation as much as angle of alpha, alpha like 90 degree, 20 degree, 45, whatever degree you decide to rotate, or beta for y, or gamma for z, for z axis. Let's have a look at that and try to formalize this as well, okay? So rotation is clear. No problem with rotation, understand? Okay, all right. So let's look at this one first. X-axis. Okay. So what I'm trying to do here. Look. Imagine you have well, your axis rotated around x. What you see here is we are standing on x-axis and we are looking down to x-axis. So we see y and z in a plane. So we are standing on top of x-axis and looking down here to see y and z axis. Now, from top, we'll rotate x-axis. Okay, you rotate x-axis. When you rotate x-axis, your y and z rotate together. Okay, you still have 90 degrees between them, and it's like rotating a frame from top. You look at frame and you rotate it, and you see the rotation as here. Okay, so if you have a point, like P on in y-axis, in XYZ axis, okay, in the original axis, all right? So in the original one, so I use red for this one. In the original one, the coordinations of this is y, p, and z, z, and z, p. yp, zp, okay? And also x. But tell me, before I continue, what do you think? Does x change? Does x of the point change of the point will change in this rotation? See, your x-axis it rotates, but its rotation doesn't change the projection point of the point you have. So no change in x-axis. So your x-axis, actually, the projection of the final point as you have on x-axis wouldn't change, will be the same, because x-axis is standing like this, coming up like this. Your point is here projected to this level. If you rotate it, it doesn't make any change. So x will stay the same, but y and z will change. Y and z will change. So the question is, if I know the location P in X and Y is XP and YP, what would be the coordination of P if I call it P prime or P in the prime system? Y prime, Z prime. What is the coordination of that point in X and, in the prime system? Okay, so look at that. See, if I project it in the new system, after rotation, my x will become to x prime p, and my y becomes y prime p. Can you find any relationship between this new point called x prime p and y? What is the relationship between these? What is the relationship between these two? Well, it's definitely related to alpha. It's YP and I'm sorry, yes, it's YP. Sorry, this is my mistake. Thank you very much for the correction. So this is Y and this is Z. Yeah, thank you. I have to change these two as well. That's okay. Just this is Y and this is Z. Very much. Yeah, you're right. So what is the relationship between this new? What is XP? What do you mean by XP, Burhan? Can I do any other mistake? Yeah, everything goes all around XP, but XP is fixed here. XP doesn't change. Yes, is exactly fulcrum of the rotation. So X rotates around itself, but the projection of the point on X doesn't change, right? Because X is not rotating this way or this way, rotating around itself. So the projection point will be the same. Your point is, for example, if you have, if you have your original point here, so I have to correct it though based on what Burhan says. So my original point is XP yp, zp, and p prime will be x prime p, y prime p, and z prime p. Yeah, I have missing p. But these two are same. They are not changing because you are rotating around x. Okay, so x, we know that xp is equal to x prime p in this case. But we are looking for a relationship between these two guys and these two guys. So definitely everything is around x, this alpha angle. So this alpha angle has a very, very, very important role. Very important role. So if I have alpha here, I will definitely have alpha here as well. And I have alpha here as well. Okay. So if I look at what I have here in terms of alpha, you see the difference from moving from here to here. The change between these two is well, has a very, very, well, I don't know to say simple or beautiful relationship, as you see. Okay, as you will see. So actually, if you want to understand what's going on, you say that your x, I would rather put this x here. So here, doesn't matter. This x is related to x prime, y related to y, and 0 relates to z or others. Okay, so look. In this rotation, what is the relationship between x and x prime? They're same, right? They are same. That's why, so what is the angle? What is the angle between your current x and your next x? 0. That's why you have cosine 0. What is the angle between current y and next y? Alpha. And what is the angle between your current z and your rotated z? See? Okay. What is the angle between your x and your y? 90 degree, right? Because x is not changing. So your x is on top. So look at this. X is coming out and your y is rotating, but it doesn't matter how much you rotate. Y is always perpendicular to x. Has a rectangle 90-degree angle with x. So it's like this. See, this is my x, this is my y, right? It doesn't matter how much I rotate it. It doesn't matter how much I rotate it. This angle is always 90 degree. Is always 90 degree. That's why what you have, what is the angle between your current x before rotation and y after rotation? It's 90 degree. Still 90 degree. No change. What is the angle between your current x and your z or z after rotation? 90 degree, because same thing, z and x are perpendicular. Angle between them is 90 degree, no change. Oh. Difficulty or the beauty comes in the next few two columns, okay? What is the angle between your y before rotation and x after rotation? This one. Your y before rotation and x after rotation. 90 degree, because same thing. Original x and x after rotation, they both are on the same on the same axis. Okay, so doesn't matter how much you rotate, this will stay the same. What is the angle between your y before rotation and y after rotation? Alpha. That's what we had. Okay, now this one, what is the angle between your y before rotation and z after rotation? Look at this. What is the angle between y before rotation, this one, and your z after rotation, this one? What is that? What is the angle? So you have one 90-degree here and one alpha here, right? Alpha plus 90-degree. True? So angle between these two. Alpha plus 90-degree. So everything is cosine. Everything is cosine. And the angle is angle between before and after. Before and after. After rotation. Before rotation, after rotation. Cosine of the angle between this axis and so how many axes I have? I have 3 axes. So 3 axes before rotation, 3 axes after rotation. How many combinations I can get? So how many combinations I can get? 9 combinations. That's why you have 9 components here between every axis. I hope that makes it very easy to understand. Now look at the last column. What is the angle between z before rotation and x after rotation? See, z and x between x, which is coming out of my plane, right? When I look at this, here is coming out. No, I'm coming out. So the angle is 90-degree. 90-degree between this and this. Between these two. So what is the angle between z and y? Z before rotation and y after rotation. Look at that. Z before rotation, remove that, here you go. Z before rotation and y after rotation. Here. What is the angle between these two? This angle. Can you see the angle? What is the angle? Originally it was 90-degree, and you took away alpha. It's 90-degree minus alpha. So the angle between z before rotation, this one, and y after rotation. So that's what we have. Cosine of 90 minus alpha. 90 minus alpha. And what is the angle between z before and after? Is alpha. So your matrix, rotation matrix, will be this. If you simplify cosine of 0, how much is cosine of 0? Cosine of 0, how much is it? 1. How much is cosine of 90-degree? So we replace this. These are simple. So this one will be 1, this one will be 0, this one will be 0. Here. Cosine of 90 will be 0, cosine of 90 will be 0, so that's why I have 0 here. So this is very simple. And that's what I expected, because our rotation was around x. Nothing changed for x. X is sitting at the same place, just turning its face around. That's it. No other changes. It's not rotating. The major change goes to y and z, goes to y and z, as we had here. See, x is x, no change. Y and y prime, z and z prime. So here, what I get, if I simplify, cosine of alpha is cosine of alpha, no simplification. Cosine of alpha is cosine of alpha, no simplification. We know from trigonometric equations that cosine of 90° minus alpha will be sine of alpha. We know that already from trigonometry. Sine of alpha. And we know that cosine of 90° plus alpha will be negative sine of alpha. We already know that. Okay? So that's the rotation matrix for rotation around x-axis. Look at this matrix now. You see, it's becoming beautiful, more beautiful. Compare this with H, which we had before, just for translation. In H for translation, this part was identical. Now it's not. Now it's not, because we have rotation around x-axis. This is for rotation. See, this part is same. No change. Do you see any value here? No, because we are not moving translational. We are not moving linear. So this part is 1. So now we are covering the other part of the matrix. Before we had just this part for linear movement or translational, and this one was for rotation, if you remember. So now it's rotation part. We are looking at rotation part, and since it's for x-axis, you have this. Any question on this, please? Okay. Now, if I ask you, there is a point, like, for example, if I tell you that there is a x, if I tell you that in my three-dimensional space, I have a P located at 2, 3, 5, and I'm rotating around x-axis for the 5 degree clockwise. So this was, I had to say that, I'm sorry. So here the positive rotation is defined based on right-hand rule. Right-hand rule means when your thumb is in the direction of the axis, and your fingers show the rotation direction. So keep that in mind. That's positive alpha. So what we when we talk about alpha is in the right hand side rule, or look at x-axis, probably more clear. In x-axis, if you have your thumb in the direction of x, z-axis, in the z-axis, if you have your thumb in the direction of z-axis, your fingers show the direction of rotation. This is the angle. So when I say, if I say 45° positive, if I don't say anything, any number, means it's with right hand rule. So what would be the point after this rotation? Can you do the calculation, please? So this point P prime, 2, 3, 5 after rotation. Okay. X, do you expect any change in X? So around x-axis, no change. 2. Okay. So the only 2 other we change are 3 and 5, and we have to do the calculation for those. So this will be So my y prime will be, based on this equation, will be 3 cosine of 45 degree minus 5 sine of 45 degree. And my z prime will be 3 sine of 45 degree plus 5 cosine of 45 degree. Can you do this calculation for me, please? So after rotation, so Nikita says it would be 3 and 4.24. So please, others, also double check. X is 3. Sorry, what? X won't change, Nikita. What do you mean? Oh, X is 3, but X doesn't change. Why did you change X? X is 2. X is 2. Yeah. 3 cosine of 45, negative 5 sine of 45. Yeah, that's all right. Can you please do the calculation for this? After rotation, y will be negative. That makes sense. Negative 14. And z will be positive 5.66. You see, you have the original location. After rotation, Nikita suggesting something different. Nikita, she should, okay, it's negative 4 point, I think you are forgetting. Yeah, I think you've done a mistake, Nikita. So y should be twice of that, actually. Yeah, Gino also. So 3, 0.7 times negative 2. Yeah, that will be. All right, so. Okay, it's all right. It's okay. So this is in degree, but that's the way we do the calculation. Now you can rotate every point. If I give you a point and tell you that we are rotating this, system, this axis, this system of coordination around X for this much of degree, you can find out what would be the destination, what would be the result. Okay. Thank you very much. So here, same thing, just equation. As you can see, the different angles are represented and showing the rotation. This is for one of the rotations around x-axis. Okay, we can do the same thing for y-axis and z-axis as well. So for y-axis, when I rotate, now we look into y-axis from top. So I have x and z, okay? X and z. If I rotate for beta, because again, right hand rule. Yes, I think negative, Josh. It should be negative. Yeah, it is. So the number is right, but it's negative. Yeah, thank you. Yeah, this is correct. Now for, if you look into y, rotation around y, with the same approach, with the same kind of mentality we had with the other one, we rotate our coordination system around y. So with the angle of beta, with the angle of beta. Do you want to have a break? Because it has been like 1 hour and a half I have been talking. Yes, I think it's too much. So we will be back like 15 minutes, okay? All right, so I'll stop recording.